Okay, so we will continue with our discussion on linear programming. So we will solve one more problem. We will revisit a problem which we formulated earlier, okay, so that it strengthens your understanding of how the algorithm works, right. So this is what is the problem number? 40? 40, okay. So you can take it as problem number 40. So we are familiar with this problem. This concerns an ethylene refining plant. It receives 500 kg per hour of 50% pure ethylene, and it refines it into two types of output. Type 1 has 90% purity, while type 2 has 70%. Raw material cost and profit, everything is, selling price is given. There are constraints in the form of packaging and transportation. Packaging facilities, how much can be packed, okay. So per hour, and then the transportation cost for type 1 and 2. So we formulated the optimization problem in one of the earlier classes in the semester. I said at that point, do not try to solve the optimization problem. To ensure uniformity, declare the mass flow rate of types 1 and 2 as x1 and x2. We have plotted all the constraints. X1 and x2 are the two types of output. We declared the two types of output as x1 and x2. So please plot these constraints, a graph sheet, and try to get the optimum. So I will just change the problem formulation. Essentially the same problem. People who have not got the graph sheet, how many of you haven't got? Does everyone have one? Okay. It should be there in your notes, right? We have already done this. Okay. So let us now that we have some scale like device, so we can use this. Okay, so 100, 200, 300, 400, 500, 600. Okay. So you have to plot all the constraints. First identify the feasible region, and then plot an iso-objective line and move the iso-objective line till it cuts the feasible region at the farthest point, because you are moving away from the origin, because when you are moving away from the origin, each objective line, iso-objective line, represents a higher and higher profit. A higher and higher profit, highest profit subjected to the constraint, that is what you are seeking, okay. So there are two constraints in this problem. Max, why? Selling price is 200 per kg, so 200 x1 plus 120 x2 minus the raw material cost is 40 per kg, okay. 500 into, you are buying 500 kg for the raw material, minus 500 into 40, correct. subject to, first is the packaging constraint, is there one more graphing pad doing the rounds? I gave 2 pads, what happened to the other one? Is it done or there is still some sheets left? Yeah, Vaibhav, you have to get those sheets. Or transportation cost was how much? So we changed it 192 x1 plus 10. Yeah, I hope all of you are able to get this. The selling price is 200 per kg for x1 and the selling price is 120 per kg for x2, right, but there is a transportation cost involved which is 8 rupees per kg for x1 and it is 16 per kg for x2, right. So you have to put 200 minus 8 and 120 minus 16, this is only the transportation cost, then you have to subtract the raw material cost which is 500 into 40, right. So this is the subject to x1 is less than equal to 200, x2 is less than equal to 225. So these two constraints these two take care of the constraints involved in the packaging. Now there is a mass balance constraint. What is the mass balance constraint? 0.9 x1, x1 has got 90% purity plus 0.7 x2 must be less than equal to 0.5 into 500. Okay. What about the transportation cost? Eight x1 less than equal to 4000, okay, right. Now x1 is, I have to plot so I can choose a region only here, correct, because it is x1 okay, and of course non-negativity constraints x1 x2 must be greater than or equal to 0. So first we have to identify without plotting the constraints, other constraints itself we have got, without plotting the transportation and packaging constraint we have a restricted region, already the feasible region is reduced. Now we have to put in the constraints. So 0.9 x1 plus, can you plot that? 0.9 x1 plus 0.7 x2 is less than or equal to 250. Where does it cut the, x axis? We plotted, no, we worked it out in one of the earlier classes, right? Tell me, 250, 275 is it? 2 okay, 250, 277 and x2 correct, 357. Now we will use the same scale. So what is this? All right. Now the other constraint is we will use the brown color. Other constraint is 8x1 plus 16x2 less than or equal to 400. So x1 will be equal to 500, right? x2 equal to 250, correct? Now we will use the blue color chalk. We will use a blue color chalk to identify our feasible region. Okay. So this feasible region has to enclose all the lines, chocolate brown, blue, and the horizontal and the vertical white lines, right? So that is our, so we have to evaluate how many corner points are there now. I told you there is a property for linear programming problems where you will have to search only at the vertices, right? That can be proved. If you take a LP course, somebody will prove it. So A, B, C, D, E, F. So there are 6 vertices A, B, C, D, E, F. So you evaluate the objective function at each of the 6 vertices. One of these is a trivial solution, x1 equal to 0, x2 equal to 0, profit becomes minus because you bought 500 kg of raw material, you did not do anything with it, okay. That is a trivial solution. Anyway, you can for the sake of the record, you just work out the solution and say that profit is minus. Then you evaluate the y for all the other solutions, and invariably it is that the solution will be that which is farthest from the origin, because the iso-objective lines will move in this fashion. Now how will the iso-objective lines look like? Yeah, take one iso-objective line. Please take x1 equal to 500. Can somebody do that? X1 equal to 500 and x2 equal to 2. Abhinandan, can you do this? X1 equal to 500. X1 is equal to 500 and x2 equal to 2. No, x2 equal to 0. What will be y? Sorry?
X1 should be less than 2, 3.
No, I am drawing some line. I want to know the slope of some line. Okay. I want to draw a line. Okay. What is the y? Okay, that is what I am saying. Y value 20,000 is will come, man. Okay, y value is 20,000. So this will be totally, it will be 40,000, right? Take y equal to 20,000. That's a good way to start with. Take y equal to 20,000. Add this 20,000 to the left side. So 192 x1 plus 104 x2 will be 40,000. Tell me 2 points. We can join these 2 points and have a straight line, and then we can move this line up and down. Correct? Okay. But even in the exam, I expect you to draw all the constraints, and I expect you to draw at least one iso-objective line, so that I know that you understood how this thing works. Even without that, you can just evaluate all the vertices and get it, but that is not completely a graphical method, right? I want you to draw one iso-objective line. Please remember, one iso-objective line you have to draw. Can you tell me x1 and x2? Which is 0? x1 is 0, x2 is Okay. Huh? So this is very crowded. Okay. 208 is it? So this is a okay. So this may not be clear. Please look at the board. This is a profit of 20,000. Okay. So you will get iso-objective lines which are parallel to each other. So when you move like this, you will get profit less than 20,000, 15,000, 10,000 like this. Okay, but it cannot go left of this because x1 x2 have to be greater than 0. Now you can keep on moving it till it just escapes the feasible region. When it just escapes the feasible region, since it is a convex polygon, since it is convex, it will touch the feasible region at one point, or it could touch at several points if one of the constraints is parallel to the iso-objective line, in which case you will get alternate optima. But in this case it does not happen to be so. So I guess E must be the solution. Is that correct? E is the farthest. So I think when you move like this, it looks like E is the solution, right? This is the graphical method, but in the exam you can just draw one iso-objective line and just say that when you move it, it will meet, but the exact solution can be worked out by finding y at A, yb, yc, yd, ye and yf. Please do that. Okay, is that clear? So there will be a question on linear programming in the exam, 10 to 12 marks. I think all of you should be able to crack it. One on golden section search or Fibonacci method will be there, and one, so straight away out of 100 you can get 22 marks. Do not mess up these two. Do not go to Lagrange multiplier. First take the linear programming and solve it. Huh? Okay, first take the linear programming, then go to the golden section search, then you pass the course. Then aram say you do whatever you want. Okay, do not give me trouble. Because last 10 years nobody has failed in this course. Okay, so this is the okay. Now YA so A is 0, no? A is minus 20,000, that is very bad. Chaitanya, you are awake? Okay. So what is B? B? Abhishek, did you calculate? Yeah, why didn't you? Huh? 3,400, all in rupees. C. C is how much? Alok, did you get it? F is easy. Tell me what is F? C is 13,000. Okay. D. D should be more, I don't know. Huh? Huh? 25,000? 90. Okay, 25,090 is it? Okay. Because of the decimals. Huh? Okay. E must be? Okay, good. F? 18,000? Okay. Now you evaluated y at the 6 points. Now you know where y is maximum. That is the optimal solution to this problem. This is how you solve this problem using the graphical method. you can introduce slack variables S1, S2, S3, S4 like what we have discussed in the previous class and solve it algebraically also. A very efficient method of introducing slack variables and solving it efficiently is called a simplex method, which can be used for any number of variables and any number of constraints, so long as both the objective function and the constraints are written as linear combinations of the variables. Okay. So at the optimum x1 plus equal to, what is x1? 200, 100 in appropriate units kg per hour, right. Can we switch this off, but I will use it again. I want the board now. Okay, so we have solved two problems. So this gives you a good idea of linear programming, right. It is very popular. It is in fact it so happens that yesterday one of my students, some of you may be knowing Parv Sharma, he called me from Singapore. So he is working for Unilever. So they have a problem. So they are getting some raw material from 28 suppliers located in 25 countries, some 20 different items, and then they are trying to minimize the cost, and then he says, sir, I want to know some optimization technique. I said, you go to the Google and get a free to download LP. So he wanted to know whether he has to use some other technique. I said LP will work, and he is working on it. So if you don't get the answer, you call me back. So people are using LP, man. So okay, so Unilever is interested. When I tried to call him back, I got 3 missed calls. Generally professors are very poor in picking up calls, right. So we are either at home or in the office, so we don't travel that much. So then I called back, then it says this number goes to Unilever Singapore, it is busy, and I don't know what why I should, I didn't do anything in Singapore and nobody when you some odd number it. Okay, so I called back. Then I was in Bangalore yesterday, so when I was going to the airport, this guy called me and said that he wanted some clarification. Okay, now we look at some other special techniques. One of them is the dynamic programming. So it is a applicable to large problems that can be broken down into stages. A complex problem can be broken down into stages, and you look at the optimal solution for each of the substages and keep proceeding. Okay. The belief is if you continue to subdivide a complex problem into stages and you optimize each of the substages, when you reach the end, that is from start you go to the end, the overall optimum you will get. So this can be proved for certain classes of problems, and this was discovered by Richard Bellman. Applied mathematician, and he was a professor of applied mathematics in University of Southern California, right. So it is called the Bellman equation. He figured out the Bellman optimality theorem, Bellman condition, and so on, right. So example, in process industries, when we use in process industries, when we use a series of heat exchangers, compressors and so on, okay, what is the minimum cost of transportation, okay, like that. When in process industries, when we use a or you want to lay a gas pipeline between two cities, and for if you want to lay a gas pipeline between two cities, but you want it to pass through some intermediate cities so that you won't have quality control and all that, and then there are various ways to go from one city to the another city through these intermediate cities, which will be the optimum path for going from one city to the another city, okay. So this will be, so what you do is in each you subdivide that while going from city 1 to city 2, in between you have got 3 other cities A, B, C, then what is the shortest path from 1 to C, what is the shortest path from C to D, D to E, stage wise you optimize, so that suboptimal solutions at each stage, suboptimal solutions are eliminated. This way there is a computational gain. What is the funda? I told you, optimization is all about trying to get the optimum without working out all the possibilities. If all the possibilities have to be worked out, it is called exhaustive search, it will no longer be called dynamic programming. So there is a computational gain or the simulation gain, we say in simulation we call it simulation gain, here we call it as a computational gain. The computational gain is what is the gain you achieve with respect to performing an exhaustive search. For problems involving many such networks, it may be extremely complicated for you, it may be the problem may be so formidable that it is impossible for you to do a exhaustive search. So this dynamic programming is also used extensively by computer science people, okay. And example, this is one example. Then the other example is transportation of goods from one place to another. Of course, there are some constraints that it has to pass through some intermediate cities, there are only some fixed paths, and for each of these fixed paths you know the cost and so on, alright. Now it can be mathematically derived and we can have an algorithmic approach, but we will just take up a simple problem and then using a common sense solution without going through rigorous numerical evaluation of the functions, objective function and so on, the technique will become very clear to you, right. Dynamic programming is also used in the Duckworth-Lewis method. What is the Duckworth-Lewis method? No unsuccessful, right?
Some Indians came up with a better method.
It is published in which journal?
On ESPN they mentioned.
Oh, no, maybe it is. But Duckworth and Lewis, they use dynamic programming, and this paper is in the Journal of Operations Research. I have this paper, I will show you towards the end of the class if I have time. Basically there are some control variables, they are optimally dividing, right. In the 50 over match there are 10 wickets, how much some team will score. If you have only 40 overs and 10 wickets, 40 overs and 6 wickets, and so he has an exponential distribution for each of these. There is a double exponential distribution and he worked out, and using past data from rain interrupted matches, Duckworth and Lewis figured out what should be the constants of these curves, and then they convinced the Wales and what cricket board, then ICC, and then they tried it and now it is, and then lookup table is available, so you can't expect umpires to solve dynamic programming problem. Every day they have to take quiz, so it is easy to implement, and it has been successful. Of course, if there is some other better method which comes up, then already so many people, there was an average run rate previously, ARR, average run rate was used basically for people who don't know cricket. So this Duckworth-Lewis method is used to determine the target for the team playing second in a rain interrupted match, okay. So I don't know, for T20 it does not come, right.
They use the same data, 5 overs, minimum 5 overs.
Oh, okay. So anyway, now so the increasing use of mathematics and operations research in sport, right, in cricket also, fine, okay. Let us take an example. Problem number 41. determine the minimum cost of transportation of goods, determine the minimum cost of transportation of goods from city A to city B, determine the minimum cost of transportation of goods from city A to city B while passing through one node each, NODE, one node each of B, C, D, B, C and D as shown in the figure. One node each of B, C and D as shown in the figure. A lot of you are putting up blank faces, so I think for strategic reasons first I will draw the picture and then continue. Okay. So 41. Okay. So you start from city A, you want to go from city A, you want to go to city B. Okay. But the funda is you have to cross through, there are 3 intermediate stages you have to cross. Okay. So there are 3 possibilities here. C1, C2, C3, D1, D2, D3, E1, E2, E3. Okay. So several paths are possible, right? This is one path, right? This is one path. There is the RG path. Oh. But actually I may give C2 D2 very high cost so that it does not work out, right. So okay, then you can go from A to this thing, then you can go from here, 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 you can go from here. Did I miss out anything? But you can't jump directly from C to E, or for strategic reasons you have to pass through one of the C's, D's, and that is why through one of the nodes, either it should be C1, C2 or C3 at this stage, it should be D1, D2 or D3 and E1, E2. Now we want to find, we will assign cost. What is it may be the cost of laying the pipeline, or in this case transportation of goods, it may be the cost of laying the pipeline. C2,
C1 to
E3, yeah.
that is not allowed.
C1 to D2.
C1 to D2.
C1 to D3.
That is also not allowed.
Why is C1 to D2 not
Yeah.
allowed?
Go from C1 to D3.
C1 to
D2.
D2.
see that is allowed, correct.
C1 to D2.
D2.
C1 to D2. That is what you do.
Yeah, please draw the, how many paths are there? 27 paths are there. If you draw 27 paths, we will go wild. So we will just indicate. Now the funda is, if you are able to calculate all the 27, there is no need for dynamic programming. But imagine that instead of 3 choices, you had 6 choices or 7 choices. Or instead of C, D, E, you have 7 intermediate stages, then you will not keep on doing it. You will not, and if the objective function also involves some calculations, then it is worthwhile to develop an algorithm for this. Now, so this is 70, you can take this to be in thousands of rupees or whatever, okay. But we will take it as 70, 60, the cost is 70, 60, 90, and this is 100, 60, 70, okay. So we will continue with the problem. From city A to city B, while passing through one node each of B, C and D as shown in the figure, the costs in appropriate units, some costs in appropriate units are given on the figure, and the rest are tabulated. I will give you the table. Some costs in appropriate units are given on the figure and the rest are tabulated. Using DP, dynamic programming, using DP determine the optimal path to minimize total cost. Using DP determine the optimal path to minimize the total cost, right. I will give you the other cost. C1 to D1, D1 to E1, C1 to D2, D1 to E2, C1 to D3, D1 to E3, C2 to D1, D2 to E1, C2 to D2, D2 to E2, C2 to D3, D2 to E3, C3 to D1, D3 to E1, C3 to D2, to make matter simple, we have assigned C1 to D1 is the same as D1 to E1 and so on. I will give you the cost 40. All right, so all the costs are given. Now you have to apply the algorithm, right. Now I will show you the first step and then it will become very clear to you. The problem has to be subdivided, right, into stages. So you have to find out the cost from A to any D first, okay. Because the final optimal path must pass through either D1, D2 or D3, okay. First get the total cost to reach any D, right. How many paths are there? No, 3 into 3, right. There are 9 paths. So there will be a tabular column with 9 entries. Then we will start proceeding from there. So the first step is dividing into sub problems. So we will say cost from A to any D. Okay. So cost through cost to D1, cost to D2, are you getting the point? You have to evaluate the cost from A to any D. A to any D can be reached by starting from A and taking any C or any D. There are 3 possibilities of C and 3 possibilities of D. So there are 9 possibilities: A C1 D1, A C1 D2, A C1 D3, correct? A C2 D1, A C2 D2, A C2 D3, A C3 D1, A C3 D2, A C3 D3. You evaluate the 9 entries, right. So what is the cost? First entry 110, 110. So this is 70 plus 40. So A C1 D1, look at the board, A C1 D1 will be A to C 70 plus C1 to D1 is 40. So this is 110, fine. A C1 D2, 140, A C1 D3, 190, good. Yeah, please tell me the other entries. Very good, 130, very good, 220. Is everybody through with this? Pretty straightforward, okay. Now we have to circle the optimal, circle the optimal path to D1, optimal path to D2 and optimal path to D3. At this stage it is too premature to look at the minimum and then proceed only from there, because we do not know what is the story from D to E. So we should not try to get premature convergence by going to local optima, but one thing is one thing is pretty sure, if you want to reach the end it has to be through any D, okay. So to reach each of these D's, what is the optimum path? Once you determine the optimum path from each of these D, when you go from D to E, you will use only the optimal paths and the suboptimal paths will be left out. That is the dynamic program. It will be very clear now. What do you want to circle here? The lowest cost to D1. Okay. Are you getting the point? Cost to D2, 130. Cost to D3, 150, correct? Now cost from A to any E. Till the evaluation of these 9 entries, no dynamic program, we did not apply any algorithm. Now when I circle this, I applied the algorithm already. There are two things, I am looking at the minimum cost to D1, D2, D3, but I am not looking at the minimum cost in the table and removing the other things. That may result in a suboptimal solution. These are the two cardinal points in the dynamic programming, okay. So now how do we reach E1, E2 or E3? It has to be through either D1, D2 or D3, alright. But when I reach from D1 to E1, the other parts like AC2 D1 E1, AC3 D1 E1, I do not evaluate because I have already eliminated that. There is no point in calculating again, then it is exhaustive search. Because anyway up to D1 I know what is the optimal path. Why do I have to worry about suboptimal paths by the time I reach D1? That is dynamic programming. Are you getting the point? So now D1 to E1, 110 plus, good, 150, 150, 180, 230. Rajesh, you got it? Second one, 200, uh, 280, okay. Here it is 180, here we may have 2. Okay. Now we want to use this. Now through E1, suppose we want to calculate the total through E1, already it is 150, it is 150 to reach E1, 150 plus 100, 250, correct. Through E2 it is how, 180 plus 60, up to here it is 180 plus 60, 240. E3, so the optimal path is A, C1, D1, E2, B. It is not A, C1, D1, E1, B, right? Because anyway we can change the coefficients. So the control variables were basically the cost associated with each state, each step. but in the cricket match there are two control variables, number of wickets in hand and the number of overs. So it will be lot more difficult. So they must have written a program and solved it, and so you can have any number of variables. Here is simple one variable. Okay, for the cricket match there are two variables. The resources of a team is basically dependent on two factors, the number of wickets and the number of overs left. Okay. So what is the advantage? What is the big thing we have done? How many evaluations did we do? We did 9 here, we did 9 here, 18, and we added 3. How many evaluations? 21. If you did an exhaustive search, how many evaluations? 27. What is the computational gain? 6 on 27. Are you getting the point? So there is a reduction of 28.52% effort because you apply dynamic programming. At each and every stage you identify the optimal solution, and at a subsequent stage you carry over from the optimal stage left behind in the previous stage, and there is no distinction between the start and the finish. You could have started from B and then found out what is the optimal path from B to E, B to D, B to C, B to A. It will give the same solution. It does not matter whether you start from left or whether you start from right. At each and every stage, whatever is the optimum you get, you proceed from there and discard the suboptimal solutions at a particular stage. But do not discard because necessarily it has to be through 1 D1, D2, D3. Do not remove all the things and look at the minimum. That may result in that may actually mislead you. Are you getting the point? So this is computational gain. Six on 27. Okay, can I quickly have the? I'll just finish in 3 minutes. I think I encourage you to read this interesting paper by Duckworth and Lewis. Okay, a fair method for resetting the target in one-day matches. So this is the Journal of the Operations Research Society, 1997. So they are from UK. So, where is the percentage here now? Okay, so the game of mathematical modeling in sport, you can see Clark, and they have used dynamic programming to assist in. Basically they are saying that the use of mathematical modeling in sport and cricket has increased. Okay, so that is this thing, and how other people have used DP and all that. So the key here, this is the key figure for the Duckworth-Lewis method. So the number of runs which a team can score, average number of runs attainable, is basically a function of two variables, the overs remaining and the wickets in hand. Okay, so in a 50 over match, if you have 30 overs left, if you have 9 wickets left, so therefore 0 wickets lost is a top and all the wickets lost is a trivial solution. Okay, so it goes exponentially like this. Okay, so the resources are two resources, it's either the wickets and the number of overs. So they have put an exponential model z of n, z n 0 z 1 minus e to the power of minus beta n, and p, they have put a exponential for this, and they say that confidentiality agreement will not tell us how the data was, how the constants were fixed and all that, but no, they say that. I will. Commercial confidentiality prevents the disclosure of mathematical definitions of these functions. They have been obtained following extensive research. They write, so that partial derivative and all that. Good to know, right? So much of mathematics in cricket. Okay, so this has not been challenged. Some of you are doing your MS or PhD in OR, then go ahead and write a paper which will tear this apart. Okay, so this is the, and so you can see that dynamic programming is very much used. So this is our the Bellman equation and Richard Bellman, right. The principle of optimality says an optimal policy has the property that whatever the initial state and initial decision are, this is basically from wiki, the remaining decisions must constitute an optimal policy with regard to the state. That is what we applied, right. Regardless of the initial conditions, when you reach a particular state, at that state whatever is optimal, for the next stage you carry over from that optimal stage, do not keep evaluating other suboptimal solutions. So he was in University of Southern California, right. So he became a fellow of the IEEE for his contribution, because computer science people recognize the dynamic programming is a very useful tool, right. So tomorrow we will start with genetic algorithms.